the definition of electric current. Whenever electric charge is moving, a new physical quantity has got to be defined. And the name for this quantity is electric current. Electric current. Okay? So the best way to think of electric current is to visualize it as a river current. Instead of water droplets, like very, very small water drops, you have got yourself an electron flow. An electron flow. Okay? When do you have a strong current? Well, either one of two things. The faster the electrons flow, the stronger the current. Or the denser the electrons flow, like the more compact the small balls are moving together, then you've got yourself what? You've got yourself a stronger current. So it's either a speed issue or a what? Or a electron density issue, I would say. By the way, if you ever become an electrical engineer, uh, well, any kind of engineer, but mainly an electrical engineer or electronics engineer, you're going to have to study something called you're going to have to study material science. Material science, because often electrical engineering, you don't just deal with the circuit itself. You build the circuit, right? And you don't just build the circuit by buying something that's already made. Sometimes you actually have to what? You have to make a certain material or a certain alloy that could actually what? Have a certain resistance or conductivity to it, which means you need to understand what? Chemistry to understand what? Solid state and basically what? Electric. Because someone might say, should we make a wire out of copper or nickel? I don't know. What kind of physical properties do you need? Guess what? You needed to know chemistry after all, because nickel offers a different number of electrons than silver, than copper, than iron, for example, and so on. So material science is very, very important. That's, by the way, how they make these like advanced chips and silicon chips and so on, by actually making sure they got a certain material that could electrically conduct without frying, like without actually bursting into flames. Oh, like okay, everyone, like okay, when they were moving fast. Oh, you know what? Everyone, check this out. Everyone, check this out. This is an amazing app. These are people with physics and computer science degrees who built this. Check this out. Everyone, do you see the current moving? How can you prove there is current? By measuring it, right? And we will measure current. Do we have the box here? Have you ever heard of voltmeters and ammeters and multimeters? Yes, we've got a whole box here. Analog, not digital, but yeah. Yes, these ones we're going to use next week. These yellow ones, they have what on them? They say what? Milliamperes. Ampere measures what? Current. So these are the ammeter or ampemeter. They just call them ammeter. These blue ones, what does it say on it? Volts or millivolts. So these measure what? Voltage. Okay, so we're going to use these next week. Okay, check this out, everyone. I have the two devices already here. I have a voltmeter and I have a what? Ammeter. I'm going to prove to you there's what? There's current here. The problem with an ammeter is you cannot just, everyone, check this out. A voltmeter is good. Look, I can just what? Move the lead here and move it anywhere else I want. I got a voltage. What's the voltage between these 2 points? 14.78 volts. But you have to touch in how many spots? No such thing is volt at a point. Nope. See, it's telling you, okay, come on, where's the other point? I need that difference between 2 points. So you can go here, or you can go here, or you can go here. You see, have you ever seen an electrician always just, walking and just touching, tapping? That's exactly what they're doing. They're basing one reference point, and then they're tapping, and it measures the difference between two, okay? The problem with an ammeter is that you can't just put it. Nothing's going to happen. You actually have to what? You have to butt into the circuit. Like you have to actually cut into the circuit and insert it inside. How do you do that? You actually have to what? Cut this. And now you can what? Connect these two. Do you see what I mean? All right. Here's one connection. It latches. And here's another connection. Hey, I've got my current. It's how much? 9.77. And what's the A? A is the unit for, it's what is the ampere. Ampere, after a French physicist who actually studied current for the first time. Okay? So this all we're going to do, but with what? With these analog devices right there next week. And actually towards the end of this week as well as quick demo, right? So, okay, so to answer your question, how can I drive this higher? Oh, I can do a bunch of things. One thing I can do is what? Is make them go faster. Make them go faster. Now, how many ways can you make them go faster? Well, maybe you can what? maybe, or slower. Maybe you can what? Change this what? Change this battery. You see what's happening? What's happened to the current? Is it going down or down or up? Down because I'm making a weaker source, a weaker battery. Okay. What if I made a wire that is has more electrons to offer? Would you see more solid balls go? Sorry, more blue balls going through, or less? You would see more, which means what? You will increase the current. You see what I mean? That's why I say it's either a speed issue or a density issue. The speed you can change easily by changing the what? The voltage of the battery. The density you can't do it unless you change the what? The wire material itself. The wire material itself. Nice. Okay. Okay. So it's a density issue or a speed issue. There you go. Come on. No wonder electricity was hard to study for me in my days 25 years ago. We did not have these apps. You either had to be a genius to really visualize it in your head, or keep building circuits 24/7. Like the Yeah, but still, but again, that tells you like a picture of it. But what's really happening? Now we have these apps that are as close to the physical picture as it could be. Just beautiful. Okay. You know what? I'm going to have to teach you how to use like all the different symbols for. Oh, this is a battery. This is a capacitor. This is a light bulb. This is a wire, and so on. Okay. What is the physical symbol? Everyone, come on. What's the physical symbol for current? No, that's the unit. I'm talking. Nope. Amp is just a short way of. Sorry. Amp is the quick way of saying ampere. Say again. I. You're absolutely right. Everyone, the symbol for electric current is I. I've seen it as capital. I've seen it as small. Although I'm a big fan of using small, depending. Up to you. Okay. Yes, Ohm's law. Hmm? Oh, yeah. How many people know that I is the imaginary number in math? It's the same symbol, but just stands for something different. Question for you though: does it seem like to be a scalar or a vector? That's weird. Question: if you reverse everyone, if I took that battery, everyone, and I reverse the what? The connection. So instead of connecting the wires like that, I flip them. Would there still be current in the circuit? Yeah, but instead of going this way, it would go what? So technically, does current have direction? It does, but only if I'm interested in what? In the connection of the circuit. If I'm just connected in the amount of the current, should I treat it as a vector or a scalar? Thank you. You got it. Yes. But but factually, when you build a circuit, you need to know which way it's what. Because imagine if you build a circuit that's flowing the wrong way, what could you do to the circuit? You could fry it, right? Because you could actually be what? Instead of discharging the battery, you could be what? Charging it up, especially if you have multiple batteries in the system. One battery could dominate and burn the whole system. Electrical engineering is no joke. I've always been terrified of ever. So, okay, if you have a stronger, okay, everyone, question, listen up, guys. Question for you. Uh, Question for you. Can you have a hydraulic system with multiple water sources? Yes, you can. What does that mean? There could be one water source that could what? Over dominate the other ones and what? Reverse the flow and start what? Charge. That's exactly what. That's why one of the best ways to understand electricity is to understand what? Fluid dynamics. It's literally 90% the same thing. Oh, if it's one source, then we're done. There's only one single loop direction in it. You're good. Yes, absolutely. Remember, electric current is a scalar quantity. We're going to believe that for the rest of this course. It has no direction. Sorry. Okay, what's the equation for current? Very easy. Super easy. Okay. Now, okay. I don't know. I like what you said. There are always like multiple equations that are going to involve the same things that we look for. The equation you just said, V equals IR, that's the F net equals MA of electricity. That's Ohm's law. That's the one. Any engineer at the end of the day, sorry, any electrical engineer at the end of the day, trust me, everything they did was to just be able to apply what? V equals IR. Voltage is equal to the product or multiplication of current and resistance. But obviously to what? To insanely complicated circuit. But guess what? At the end of the day, all they're doing is V equals IR. They just have to like have a complex application way of doing it. But what about defining I itself without using V and R? That's the equation here. The equation is, there we go. The mathematical formula for the electric current in any section of a circuit is electric current is how much charge is moving, because if it's not moving, there is zero current. Done. Over time. How fast is it doing this deed? What's the symbol for charge from yesterday? Capital Q or small q, don't really care. And time, although should be delta time because it's always an interval or an amount of time. How do you measure Q again? Q in coulombs. How do you measure time? Ladies and gentlemen, I just defined for you what an ampere is. An ampere is a coulomb over a second. 1 ampere means 1 coulomb of charge. 1 coulomb of charge. How many electrons could be? 1 coulomb of charge is going through the circuit in 1 second of time. That's 1 ampere. By the way, again, do you remember yesterday what I said about how much ampere it takes to put your heart to stop? Half. Half an amp is all that is needed. Half an amp. If it makes its way to the heart through the circuit, like through the skin, that's enough to shut down your heart. Because your heart is an electric. Your heart is actually a small battery. Have you ever heard of a pacemaker? By the way, usually you hear a pacemaker when someone has a pacemaker installed, right? But your heart actually comes with a what? With its own pacemaker. A very small voltage in the milli of volts is needed to what? Give each heartbeat. The problem is a half an ampere of what? Of current could shut down that circuit. That's called what? Fibrillation. How do you reverse fibrillation? Defibrillation. Yes. Okay. All right. What's the unit again? We said it's the ampere, and it's the only unit that has a capital A. It's the capital A because it's the name of a person. Now, obviously, almost no one says ampere. Everyone says amp, 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 amp. By the way, have you ever heard the word amp in English? Yeah. What do you call someone who's super excited? Amped up. Where do you think it came from? Yes, you're right. Whenever you say someone is amped up, that means what? They have so much juice running through them. It means what? So much current. Amped up came from that. Amped up. Okay. That's okay. What do they also call current? Tech people, like industry tradespeople, usually they don't say I'm measuring the current. They say I'm measuring the what? Amperage. They always do the AGE. They say voltage, amperage, even resistance. You know what they call resistance? Come on, what's the unit for resistance? Ohm. They call it ohmage. Yep. Tradespeople just say the AGE. Voltage, amperage, ohmage. Sorry. Okay, come on, come on. Okay. Boom. The definition of a what? Of an ampere. An ampere is 1 coulomb per 1 second. Hey, did we do something else? Guys, did we do something else as something per 1 second? What was that? Yeah, keep going. Light. How do you, watt? A single watt? A single watt was a single joule consumed or produced or whatever over 1 single second of time. You got it. This is the exact same idea. A single ampere means what? A single coulomb of charge passed through wherever we're talking about the circuit. Small section, big section, but it did it in 1 single second of time. Here's my question to you then. What does 10 amps mean? What does 10 amps mean? Does it mean 10 coulombs per 10 seconds? No, exactly, because what does 10 coulombs per 10 second mean? Still 1 to 1. No, it's 10 within 1 second. Yes. You see, I told you everything transferable skills. I talk about one thing, it will make its way to something else. Okay? All right. What's the definition of the ampere? We always define it this way. The ampere is the amount of electric current that what? That is obtained when you pass how much charge? Huh? How much charge? Come on, eyes on me. 1 single coulomb of charge is passed through some region inside the circuit within a time interval of 1 second. Done. Okay, let's do a couple of demo problems. Okay, what is the current traveling through a cell phone charger that does what? That passes zero point 0.2. What's a small m? Small m. Hmm? Millicoulombs of charge. Oh, see, I never like this way of phrasing question. They're saying millicoulombs of what? I never like that. You see, either give me the number of electrons or the amount of charge. Do you see what I mean? They're telling you a certain number of electrons moved. They collectively added up to how much charge? Zero point 0.2 millicoulombs. Then call it zero point 0.2 millicoulombs of what? Yeah, because to me, I will never say that you measure number of electrons using coulombs. That to me makes no sense and it's confusing. Okay, so I'm okay with that. That's fine. But I will never phrase a question for you like that. I'm either going to tell you zero point 0.2 millicoulombs of charge, or when 1.7 times 10 to the 16 electrons have passed through. Passes the a point in the circuit in 0.75 minutes. Answer the in amperes and microamperes. All right. Do I have enough numbers for the equation? Yes. What's the equation for I? Come on. What divided by what? Come on. We just finished. Yes. So go ahead. I equals Q that passed over time it took to pass. Okay. Who knows the scale for a milli? 10 to the negative 3. So you have to write 0.20 times 10 to the negative 3. Now, is my time scale okay, or does it need to be converted? To what? To seconds. How do you convert minutes to seconds? You multiply it by 60. Okay, let's keep going. I'm going to keep it. By the way, can you write zero point 0.2 times 10 to the negative 3 in a proper scientific notation? Well, of course you can. You can make it what? You can make it 2 times 10 to the negative 4. You don't have to do that. I'm just saying if you want to. All right. Come on, calculate this for me. Go. In scientific notation, 2 times 10 to the negative 4 divided by 45. How much? Well, we already have the answer up there. It's 4.4 times 10 to the negative what? 42. I didn't know they have 4.4. What? No. No. 3/4 of a minute is 45 seconds. 15, 15, 15. Are you on hexadecimal system? Point 75. 75. Oh, you're doing 70. You're doing 70% of a minute. 75, my friend. You're good. See, 5% costs you 3 seconds. Okay. Everyone, what's the unit for that? If everything is standard, what do you get? Amps, you get a capital A. But they're asking you in what also? Come on, what's the scale? It's already 10 to the negative what? 10 to the negative? Do we already have 10 to the negative 6 on the list? Of course we do. It is already a microamp. So you just put 4.4, and this times 10 to the negative becomes micro, and the A stays as an A. It worked out perfectly. It was not like a -5 or a -7 where we had to steal powers. Nope, it was one of the ones on the sheet, on the big, large scales, small scales sheet. Done. What? No, no, remember the large scale sheet I gave you for power, megas and gigas and teras and stuff? Yeah, 10⁻6 happens to be one of them. Okay, come on, we're not done. Come on, one more demo. Okay, again, you see how they phrase it? Ali, read the question. So hold on. How many electrons measured in what? That doesn't make sense, right? Either ask me how much charge measured in coulombs or how many electrons and stop there. How many electrons result from a current of 15 amps for how long? Yeah, by the way, 15 amps is quite a device. 15 amps is a lot of current. And 24 hours is a lot of what? So imagine basically what having a machine that operates at an amperage of 15 amps and you leave it on uninterrupted for how long? A full day. All right. What's the equation here? By the way, they're asking how many electrons. Damn it. We don't have the equation of electrons today. We had it yesterday. But what equation do we have today? What equation did we learn just now, 5 minutes ago? I equals what? I equals, exactly, I'm going to rearrange or crisscross. I'm going to get the Q times equals what? I times delta T. Yes. Okay. Is this okay? Is this a good scale for this? Is ampere a good scale? Okay. Is hours a good scale? Nope. So basically, I'm going to ask you how many seconds in a day. Hey, I know that number, 86,400. You just multiply the 24 by 60 by 60. So 15 times 24 times 60 times 60. How much is that? Come on. You should you should have a big number. Come on. So okay, so Hamid, go 1, 2. Give me the digits. 1, 2, 9, 6, 0, 0, 0. In what unit is this number? Coulombs. Why? Because it's what? It's charge. But it's not asking for. Oh, hold on. We're almost done. We're not asking for the charge. They're asking how many electrons. What equation has the number of electrons in it? Q equals Ne. So right now I can just do what? N equals Q over E. Come on, let's do this before we leave. 1.296 times 10 to the 6 divided by, you remember the magic number for the charge of a single electron? Single? What? No. Nope. 1.6? You were talking about the power, negative 19. Okay, what is that? That will be 6 minus 19 is 20. It's actually got to be 24. Come on, how much? What's 1.296 divided by 1.6? I already worked out the power of 10. 8 point. Is this in coulombs or in E's? Because it's how many? Can you tell me how many electrons that is? Do you remember what's 10 to the 24? 10 to the 24 is 10 to the 12 and another 10 to the 12. What's 10 to the 12? Come on, what's after a billion? What's after a billion? Trillion. 8.1 trillion electrons move.